All right, I think now we are recording. I'll try to remove that. Remove that. And that's pretty much it. Okay, so I guess this is the official start. First of all, can you hear me at the back? Okay, it's too loud to, it's good. Okay, so let's get started. So welcome everybody to Austin, Texas, and welcome to this 2022 summer school on Electron-Phonon physics from First Principles. Okay, so my name is Feliciano Giustino. I'm one of the organizers of this event. All right, so what we're going to do in the next maybe 5-6 minutes is that I'm going to give you some details about the school, and then some logistics. All right, and then we're going to start with the actual lectures. All right, so by the end of this like kind of mini presentation, you should get an idea of, how we are organizing the event for the week. So first of all, let me tell you who is in charge here. So the organizers, apart from myself, are Roxana Margine from Binghamton. Roxana is upstairs, I guess. Emmanuel Kupakis from University of Michigan. Samuel Ponce there from the École Polytechnique de Louvain. Yunjun Lee from UT Austin up there. And then you must all have met already Annecy Liddell. She is basically in charge of the organization of all the aspects of this event. And a really big thanks goes to her for all the work she's been doing. I mean, if we are here today is, in large part thanks to her work. Let me just tell you how this started. So in practice, in around 2017, we started noticing that there was a lot of training for things like density functional theory and computational material science. And at the same time, the field of electron-phonon physics was growing, but there was no dedicated event. So we asked ICTP in Trieste, so this is the International Center for Theoretical Physics, to help us organize an event for electron-phonon interactions. And they were kind enough to host us, and then we had an event in 2018. So people were happy with that event and asked us to organize a new one. So we prepared to do something in 2020, but as you know, there's been a pandemic in the middle. So how that evolved is that we had a virtual event last year, okay, approximately same time. And then this year we decided to take a risk and have it on in person here in Austin, right? So the important something I need to tell you is about who is paying for this. So we have 4 key sponsors. So one is the National Science Foundation, one is the Department of Energy, one is the Texas Advanced Computing Center that we will visit on Thursday, and one is the Oden Institute for Computational Engineering and Sciences, which is my home institute here at UT. In particular, I need to give a special acknowledgement to NSF because they are supporting 40 of you in terms of travel, accommodation, and expenses. So they were extremely generous with that. This is not that usual. And just to let you know, some people asked us, how did you pick the 40 people who received support? It was pretty much random. Okay, so we just try to prioritize PhD students, and we try not to concentrate resources in a single group. So if there were 2 or more people from the same group, we just give one scholarship out of fairness for everybody else. Okay, so that's pretty much in terms of sponsors. Now, in terms of numbers, so actually we have 75 people registered to be here in Austin today. I think we give most badges, so this should be the right number. Then we have 18 instructors. I will mention them in the next slide. And then we have a fair number of people following us online. So the plan is to stream the morning lectures in a webinar mode because it's fairly easy. Okay, so all of this is going to be recorded. And then we will not stream the afternoon part, which is much more interactive. We will be in the room where you have breakfast, basically on the tables with laptops. So that's more difficult to stream. So this is a page with all the instructors. I'm not going to go name by name. I just want to mention a few of them. So these ones, highlighted in pink, I would like to thank them because they made it all the way from Europe to teach you. So we have Paolo Giannozzi from the University of Udine, Nicola Marzari from the École Polytechnique Fédérale de Lausanne, Antimo Marrazzo from the University of Trieste, and also Marius Zacharias from the University of Rennes. Okay, so they really made a long journey to come and help us here. Then I want to mention our friends from California. So this is Zhenglu Li, Mauro Del Ben, and Jack Deslip. These are the GW people. They will teach us about GW on Friday, and also the Berkeley GW code, and then help us with the hackathon during the weekend. Then a couple of special guests. So Tati Russo-Tate and Brandon Campitelli. These are 2 professionals here at UT who specialize in diversity, equality, and inclusion. So as you know, if you are based in the US, so NSF places a very strong emphasis on these aspects. So they will come tomorrow and essentially, run a little workshop on the subject of implicit bias. Okay, and this afternoon we'll ask you to look at a questionnaire tonight that we will discuss in this mini workshop tomorrow. I think last but not least, so this gentleman here, Dan Stanzione, is the director of the Texas Advanced Computing Center. And he's been very graciously agreeing to give a talk about high performance computing exascale on Thursday. And also his team at TAC will basically lead a guided tour on Thursday afternoon. So we will have a chance to see some of these big computers of the NSF here at Austin. So just for those who don't know, TAC is essentially the flagship national supercomputing center of the National Science Foundation. So essentially the biggest machines are here, 5 miles north of campus, okay? Schedule. So the way it's going to work is that all the information about the school will be online. So you should have been given a bag, and in this bag there should be a little card where you see this QR code. All right. So what you need to do is to just scan this code, and you will be led to the website of the school. So all the information about what we're going to do every single day is there. If there are any updates, we'll post them there. So use that as a reference. So the structure is very simple. We're going to have lectures in the morning, like this in this setting, okay, like a mini workshop, and then a lunch break, and then we will have tutorials in the afternoon where you're going to be sitting upstairs with your laptop running exercises. All right. So there are a few exceptions to the schedule. So in particular, today, after the first session of tutorials, we're going to move to a poster session just to know each other. And then tomorrow we're going to have this DEI workshop I just mentioned in the second part of the afternoon. And then on Thursday, we will visit TAC, and then we will follow that with a social dinner. So we're going to get some real Texas barbecue at that point. And if you're a vegetarian, don't worry, there is also going to be some options for you. And then Saturday and Sunday, we're going to try a novelty, which is trying a hackathon where you don't need to be worried. You don't need to be a pro programmer. It's more of an opportunity to try out the codes a bit more in detail than as a standard user. So it's a way to kind of get you excited about some of these codes. And this is pretty much everything about the schedule. Then another thing I want to mention is that on the website, Annecy prepared a page with all the amenities that you can find near campus. So it's just a very short list. I mean, if you go on the website, it's much longer, the list. Basically, these are places to eat, drink, relax, do whatever you like around campus or walking distance. And the picture you see here is something that I put there because it's essentially somebody yesterday asked me about gym facilities in the nearby. So actually, the university has a gymnasium which is literally on the other side of the street with respect to this building. So it's 2 minutes walk from here. And it's a wonderful facility. In particular, they have an aquatic center that has essentially lap pool, leisure pool, and a lot of people go there relaxing during the day. So to go there, you need to purchase a day pass, which is very cheap, and it's open up to 10 p.m. So if you want to go swim like at night, you can do it, and it's really next door basically. So the other thing, some people ask me, is it safe to walk around? Actually, it is very safe. Austin is extremely safe for kids, families, young people. You don't need to worry. Here there is some kind of links. If you want to be accompanied home in the evening, there are some services for that. But really, it's an extremely safe place. Okay, so you don't need to worry in any way. So the whole area of campus, but also downtown, it should be fine. Just avoid going 5 a.m. in 6th Street, and that should be okay. So now this is the end of it, and I just want to say that today we're gonna basically have 3 lectures in the morning. I'm gonna give the first lecture because that contains a little bit of a overview of all the topics we need to touch upon during the school. Okay, that's gonna be a very simple introduction. Then we're gonna have a lecture by Paolo Giannozzi on density functional perturbation theory, and then one by Nicola Marzari on the maximally localized one-way functions. Okay, then we're gonna have a lunch break and a tutorial on quantum espresso in the afternoon, followed by a poster session. So with this, I'm done with the general introduction, and I will move on to the first lecture, if that's okay. And maybe this is the time to take some questions, if you have any. So you're asking me to move this down. Okay, go away. Right. Okay. Yeah, right. So maybe the other thing to say, if you see people with the logo on the T-shirt, like Anne at the back of the room there, so that's basically people of the team. So feel free to ask them any questions. Look for help, and just general information, not only about the school but also about Austin, and entertainment in the area. Okay, so that's basically all we need you to know. All good? All right. Yeah. There is no need to. Okay. So let me then get started with the the first actual lecture. So today I'm going to be basically the chair and also a speaker, which is anomalous, but okay. For once we can tolerate it. So the idea basically is that we want to start now with a very simple introduction to electron-phonon interactions. Okay. And the reason why this lecture is here at the beginning is that I need to mention density functional theory, I need to mention density functional perturbation theory, one-year functions, and some very simple concepts of electron-phonon interactions, okay? So this is something very elementary. So some of you will find this concept extremely trivial, and for some of you, they are completely new. So the purpose of this lecture is just to set the stage and to establish a common language, okay? So if you're interested in advanced methodologies, those will be discussed essentially during the course of the week. We will discuss many-body perturbation theory tomorrow. We'll discuss, Boltzmann transport on Wednesday, superconductivity, and many-body equations there on Thursday, GW calculations on Friday. So there is going to be plenty of challenging things to do, but we're going to start simple. All right. So the way this lecture is going to go is that I'm going to first tell you a little bit about where we see electron-phonon interactions. Then I'm going to basically try to explain how we think about these interactions in terms of calculations, how one can approach these problems in the simplest possible way. And that will lead us to so-called Rayleigh-Schrödinger perturbation theory. The name is fancy, but this is simply the basic perturbation theory that you learn in quantum mechanics 101, the first time you see quantum mechanics, okay? And then I want to tell you a little bit about the electron-phonon matrix element, which is the core component of all the calculations, and that is what motivates much of the methodology that we will discuss this week. And then introduce very briefly one-year functions that will be then covered by Nicola Marzari and Antimo Marazza. So 4 slides to give you an idea of where we see electron-phonon interactions in practice. So the picture here on the left is just a fancy representation of a field effect transistor where there are the yellow things are gold contacts, and the thing in the middle is a ball and stick model of moly disulfide. So this would be a transistor with a channel based on a 2D material. So this figure is from the group of Andras Kish in EPFL in Lausanne. And the reason why I'm showing this picture is that when you work with these systems, one of the key quantities is the carrier mobility in the channel. So the mobility is essentially the coefficient of proportionality between the average speed of an electron and the applied electric field. And this quantity is shown here. This is measured data as a function of temperature. So you can see from low temperature to 300 Kelvin, this mobility decreases, all right? So this is a manifestation of electron-phonon interactions. And intuitively, what this means is that as electrons travel to the channel, you increase the temperature, thermal agitation increases, so you have more scattering, so the electrons slow down, all right? So that's one of the key manifestations. So a second example is something very popular. So it's something we see every day in a way, but we don't think about it. So you know that most solar panels are made of silicon. So there's an image of a kind of silicon solar cells. And what people usually do not appreciate is actually that electron-phonon interaction play a big role in silicon photovoltaics. So the reason is the following. So the black line here is the optical absorption coefficient of silicon, kind of crystalline silicon. So that means that the larger this quantity, the more light gets absorbed, right? So for a photovoltaic material, you want to absorb as much light as you can, right? So now the point is that the sun emits sunlight in the visible, so this rainbow plot here, and also in the infrared here, right? So there is almost nothing on the right side of this rainbow. Now, you see 2 features in this plot. So here there is a sharp onset. This corresponds to the fundamental bandgap of silicon, 1.1 electron volts. And then there is this knee here. Okay, so this corresponds to the first direct bandgap of silicon, which is about 3.3 electron volts. Right. So in practice, what happens is that if you were to use a standard theory without electron-phonon interaction, your optical absorption will start at this point, because as you know, photons carry very small momentum, so you don't have you cannot change the momentum, and therefore only direct transitions are allowed, right? And the fundamental band gap of silicon is indirect, so you cannot cross it. So the entire section here is entirely due to electron-phonon interactions via phonon-assisted optical absorption, all right? And in particular, this is something also that some people don't appreciate, is that these are entirely to do with quantum zero-point fluctuations of the nuclei. It's not a temperature effect. Even at zero temperature, you would have this effect here. So this will be discussed by Manos Koupakis and Xiao Zhang on Wednesday, actually. So third example, superconductivity. So this will be discussed by Roxana Margine on I think on Thursday. And the idea, so these plots are from this famous paper by the Eremets group in 2015. So what they were doing is to try to realize high temperature superconductivity in solids made of hydrogen. So to make hydrogen into a solid, you need to compress it at very high pressure. So these experiments are like hundreds of gigapascal. And the idea is that they are run using diamond amyl cells. So these are diamond tip, diamond at the bottom, you squeeze them together. So there is a gasket around to avoid the material escape from the side. So you realize an extremely high pressure, it becomes metallic, and then you can measure things like resistivity. So in this case, the resistivity goes down with temperature, and at some point it jumps and it goes directly to zero. So this is the hallmark of a superconductive phase transition. And this has to do, in this case, with the pairing between electrons resulting from electron-phonon interactions, okay? So how do people know that this is about phonons? Well, there is the smoking gun for phonon interactions is what people call the isotope substitution experiment, which is simply the following. So the compound in blue is a sulfur hydride, so there is hydrogen. The compound in red is sulfur deuteride, so hydrogen is replaced by deuterium, which has twice the mass, okay? So by doing that, the phonon frequencies decrease. And in the Bardeen-Cooper-Schiffer theory, the critical temperature scales with the phonon frequency. So if your critical temperature decreases as well, this is a signal that this might be related to phonons, and that's what has been demonstrated by many studies afterwards. And lastly, just one example from a material that has received attention lately in the area of optoelectronics and photovoltaics. If you've never seen this before, this is a model of something called methyl-ammonium lead triiodide. So lead is in the middle of the octahedra, iodine is in the corners. These are octahedra connected by iodine. And then there are some voids in the middle of the structure, and these are molecules. And this structure has attracted attention because it leads to solar cells with extremely high energy conversion efficiency. So not exactly this one, but a friend of this one, let's say. So the only thing I want to show you here is that these materials have a band gap of about 1.4, 1.5 electron volts. And this is a measurement of the band gap. In practice, this is energy, this is temperature. So how this was measured, the experimentalists here, they photo-excited, so they basically shine light about the band gap. So this, I think, was green light, about 2 electron volts. Then the electron hole recombine at the edge of the bands. And that leads to a photoluminescence peak, which is corresponding approximately to the band gap, okay? So this would be a band gap, for example, of 1.47 electron volts. And as you increase temperature, actually, you see the band gap moves, but also the signal is widening, all right? So these are both effects that have to do with electron-phonon interaction, the shift and the broadening. So we'll discuss them both in the following. So now, I guess what I would like to do is to reason a little bit in very, very simple terms about how we think about electron-phonon interactions. If you want to do calculations. So the following reasoning is extremely elementary. Okay, we'll do something more complicated tomorrow, but for now, let's start from simple things. So one could start from a kind of Green's function theory right away, but that's actually the most complicated possible strategy. So what we're going to do is to start from density functional theory, because most of you in the audience are already familiar with that, okay? And we ran calculations in the past, so we kind of know what this is about. I'm not going to give you a DFT kind of crash course. I just want to summarize a couple of key equations. So these will be Kohn-Sham equations, like kinetic energy, self-consistent potential, wave functions, eigenvalue. So usually in DFT codes, like the quantum espresso we'll use this afternoon, you solve these equations, you get the wave functions, eigenvalues. From the wave functions, you build up the charge density by summing up over the occupied states, the square moduli. And then we know from DFT that from this charge density, you can build the Hartree potential here, depends only on density, and the exchanging correlation potential, okay? Then you also have a contribution to the self-consistent field, which comes from the ionic attraction between electrons and nuclei. In this case, I'm just using the Coulomb potential. In calculations, you usually have a pseudo potential. The concept is the same. Once you have this self-consistent field, you bring it back and you solve iteratively. Okay, that's the SCF loop in every calculation you know. Now, the reason I'm showing this slide is that one could ask, okay, how do I see electron-phonon interactions in this slide? Well, the answer is that if you check, the only place where the atoms appear, so the atomic positions appear, is here. So it's basically the ionic potential, that the attraction between electrons and nuclei. So since the atomic positions appear here, so they appear in the self-consistent potential, and therefore they appear in the wave functions through the solution of this equation and to the eigenvalues, and therefore in the density. Okay, so in a way the atomic positions are everywhere, but simply because they enter through this place, okay, through this bit. So electron-phonon interactions really correspond to what happens, asking what happens if I change these atomic positions and look at the consequences of that, right? So in the previous slide, essentially, the idea was to establish that the self-consistent potential is a parametric function of the atomic coordinates. So that's a key kind of tenet of density functional theory. If you go to a many-body theory, things get more complex, okay? But for now, let's assume that DFT is enough for everything you want to do. So there's a parametric function of the coordinates. So one could say, let's try to study this function, and let's simplify things just to keep it simple. I'm going to say that there is only one atom, and it can move only in one direction. And there is an atomic equilibrium position, which is tau naught. And I consider the final coordinate to be tau naught plus a simple displacement called u, all right? So if u is very small, I can perform a Taylor expansion of this object, having the first like 0th order term, first order, second order, and so on. So this first term is essentially the potential that I find at equilibrium. So you run a calculation, you find the equilibrium structure, that's the potential that you have. So whatever follows is the perturbation that leads to electron-phonon interactions, okay? So if one asks, okay, what are electron-phonon interactions? At least what is the effect on electrons? So, well, all of that has to do with these extra terms in the Taylor expansion, right? So that's the basic idea. Now, once you have a perturbation term, the question is, what do you do with that? And the plan is basically to, try to study using perturbation theory. First of all, let me give you a pictorial representation of this term. So we start from a self-consistent field, which is periodic. So this is, imagine a solid. The black dots are atoms. So they're all equally spaced. The general potential looks more or less like that, in standard calculations. Then I move an atom a little bit. Okay, this is the U displacement I mentioned. And that causes a slight distortion of the potential here. So if I take the difference, so this difference is essentially the first, second, third order terms of this Taylor expansion I mentioned earlier. So I get something that looks like a dipole. Okay, it's not exactly a dipole. It's a little lump of charge, but it's something that more or less will have this shape in simple cases. So the question is, what do I do now that I know the shape of this object? Well, I can apply perturbation theory. So what we call Rayleigh-Schrödinger perturbation theory is basically the most basic form of perturbation theory. So it's the first version we learn in undergraduate quantum mechanics. Okay, so there are 3 recipes that we need to go through and that actually are extremely useful for what we want to do. So the first one is that a basic perturbation theory tells me what is the change in energy, in the energy eigenvalue, if I have a perturbation. And that is simply the expectation value of the perturbation over the state I'm looking at. Okay, so that's for a non-degenerate state. So just let's keep it simple. So that's a simple recipe. Then one can also tell, what is the change of the wave function. So that's a similar. The matrix 7 is a bit, contains off-diagonal terms. There's these denominators between unperturbed energy levels, and then the original unperturbed wave functions here. So with this recipe, I can tell how the wave function changes when I move atoms around. Again, very simple. So those 2 bits actually correspond to a situation where I specify the atomic displacement. And this object is a number, is a parameter, okay? It does not change with time. So this is both for static perturbation theory. So another situation one could consider is that I take this atom and I move it, with an oscillation, okay? So time-dependent oscillation. So in that case, I can no longer use static perturbation theory because there is time involved, and I need to use the time-dependent Schrödinger equation, and I need to use time-dependent perturbation theory. So in that case, what one discusses is the transition rate from an initial level to a final level. So this would be Kohn-Sham eigenstates. And this transition rate is simply given by the Fermi-Golden's rule, which is the square matrix element of this perturbation multiplied by the Dirac delta function that has the initial state, the final state, and the frequency of the oscillation that I'm considering. Okay, so these are very simple recipes, and it's something that we learn much earlier than solid-state physics or electron-phonon interactions. But they're actually the core of all methods that have to do with electron-phonon physics. So what I want to do in the following few slides is to show you how these things are useful in a number of contexts. So in particular, so the first expression is the key to understand temperature-dependent mass structures in solids. The second expression is important to explain and to calculate phonon-assisted optical absorption, but also to study the formation of localized electrons like polarons. And the third term is key to understand carrier transport, okay, like phonon-limited mobilities, conductivities, resistivities, and things like that. All right. So I will go through this example, through these cases with a few simple examples. Before going there, we need to basically decide what is the displacement. All right. So just to, if I go back a second, so you see that here there is a displacement U. This is a number. So if I double this number, my change in energy will double as well. Okay, so just staying at this level is not very useful because I can get any change I like since this is still a free parameter. So I want us to decide what is this number. And essentially, there are two ways to go about this. We will discuss only one of the two ways. So one way is that you are discussing with experimentalists who are performing an experiment at finite temperature, okay? Meaning that they have something with a temperature control and they tell you, I don't know, the carrier mobility at 300 Kelvin. So that means it's an experiment at equilibrium, and you want to study these displacements at equilibrium. The other scenario is that you talk to experimentalists to do ultra-fast experiments or pan-probe experiments. So typically what that is that they shine light, okay, in such a way as to excite selectively a specific vibration. So that vibration can have a very large amplitude, but all the other vibrations approximately don't have any amplitude. Okay, you really select specific phonon modes. So in that case, you need to go along a different path. So today, for simplicity, we stay on this side, only looking at equilibrium. Okay. So for equilibrium, actually, the situation is very simple because in many cases we're interested in, we can use the harmonic approximation. So whenever you can talk about phonons, it means that you can talk about a harmonic approximation. In that approximation, vibrations can be mapped into a set of independent oscillators. Okay. So in practice, the problem is equivalent to looking at the displacement as a function of temperature of a point of mass that is attached at the end of a spring. It's no more complicated than that. And this is actually quite easy. In fact, I could ask you in the audience if you can tell me what is the average displacement or the average square displacement. The answer is quite trivial. For the average displacement, if this is a harmonic potential, the average is 0. So you stay on the right, as long as you stay on the left. So the average is 0. So the first non-zero term is the square. So the mean square displacement is going to be non-zero. And to determine it classically, it's actually quite simple. You can use the equipartition principle. So each degree of freedom gets kT, so a K Boltzmann constant for of energy. And using that, you can just write that the mean square displacement is proportional to kT. Right? So that means that if you plot the mean square displacement as a function of temperature, you get a straight line. So very easy. And that's something that you observe if you do, for example, molecular dynamics. So you will see the displacement increase linearly with temperature. Now, this is the classical case. In many ways, we are interested in the quantum case, which is slightly different. So in that case, what one does is to take the eigenstates of the quantum harmonic oscillator and perform a canonical average. And that leads very simply to the Bose-Einstein distribution. So nothing too complicated. So the two cases are very similar. So black is classical and blue is quantum. Right? So you see at high temperature, they are basically the same. So they only deviate at low temperature where classical goes to 0 and quantum goes to a finite number because of 0-point quantum fluctuations. So at this point, one could ask, okay, what does it mean that I have high temperature or low temperature? That depends on the material. So you see here that the inflection point is basically at about the phonon frequency, right? So if you take, just to make an example, the perovskite I showed you earlier, where there is lead, which is very heavy, typical phonon frequencies are in energy units are about 10 millielectron volts. So at room temperature, I would be sitting more or less here. So those systems behave kind of classically in terms of vibrations. If you now instead you take graphene, the E2G mode is 200 millielectron volts. Okay, so if room temperature is 26, it means the room temperature will sit here. So graphene is very much a quantum system in terms of vibrations. Okay, so it really depends on the system you're looking at. So the classical approximation is not always bad. It depends on the system we're looking at. Now, what do we do with this kind of averages? So let me give you, I'm going to go through this 3 examples, energy, wave functions, and then scattering rates. And I'm going to start with the energy. So this is essentially the precursor to what is known today as the Allen-Heine theory of temperature-dependent band structures. I will not go into detail. I just want to give you a flavor of what happens. So suppose that this is not just a n as an index, is something that carries also a band index. So you're looking really at the band dispersions. And you want to know how it changes with temperature. So I need to take the thermal average of this thing. This is a number. So I end up taking the thermal average of that. But the average is 0, as I said, because it's a harmonic system. So this term disappears because we are in a harmonic system. So what I need to do is to go to higher order terms. So there are 2 options. One, I take the same term, but I go to second order in perturbation theory. So this gives me these matrix elements, these denominators, and then a U square outside, right? So if I take the thermal average of that, is non-zero for the reasons I showed you in the previous slide. There is another option that I take the second derivative of the potential, so the second order in the Taylor expansion, and then perform first order perturbation theory. So that essentially takes me to a situation where I also have U square here. So these 2 terms must be of the same size. I cannot take one or the other. So in practice, what people do, conceptually, is to write this term as change in energy equals some prefactor, it's something you can calculate, depends on the material, times U square, and then you perform a canonical average of those 2, right? So if you do canonical average, this will be depending on temperature, and this acquires this Bose-Einstein distribution on this side. So that's pretty much it, right? So there are many complications in the calculations, so many technical details, but this is the conceptual basis of all of this. So to give you an idea of how this works, what I'm going to do is to focus on this term here because it's easier to discuss. And what I will consider is that this term is not very important, just keep it unspecified. And then I'm going to replace the conduction band bottom or valence band top in this number, okay? So imagine a semiconductor or an insulator where you have 2 bands, completely filled, completely empty, valence, conduction, okay? So let's look at the conduction. So the term I showed you in the previous slide, I want to know what is the shift with temperature of the conduction band bottom here. So what I do is to replace the first term here by the energy of the conduction band. And then I try to perform this summation. So now notice is that in this summation, there will be contribution from every state in the conduction and every state in the valence. However, this denominator goes almost to 0 for states that are very close to the conduction because they are very close in energy, okay? So the most important terms will be the ones that are really here. So this will not be very, very important. Far term will not be very important. Really, the key is going to be the ones very close to the conduction band. Since we are close to the conduction band bottom, all these terms are above the energy of the conduction band bottom. So this means that this denominator is negative. Square modulus is positive, so this shift has to be negative, okay? If I look at the valence, the opposite happens. Basically, the shift has to be positive. So that means that if I increase temperature, conduction lowers and the valence raises, okay? So the band gap goes down. So this is approximately, oops, something happened here. Okay, so this is approximately, okay, I don't know what happens. So I lost a slide, but basically what I wanted to show you is that the band gap basically goes down with temperature in standard cases. Maybe I'm going to show you with this example. So what happens that if you take, I will discuss this in a second, but basically what happens that if you take a band gap of a certain material and you increase the temperature, you typically observe that this band gap decreases, okay? So you remember the example I gave you in the slide of the perovskites, the band gap was increasing there. There was an anomalous case, which is quite interesting, and it has to do with the specific vibrations of perovskite lattice, okay? But in most cases, we know, basically, as you increase the temperature, the band gap goes down. So this is basically an example from a calculation that will be discussed by Maria Zacharias on Friday. So you will do this kind of calculations. In particular, here you have the example of silicon, which is pretty simple. So these lines are the bands, so valence band, conduction band, and the black here is the band structure you would calculate using density functional theory, okay? So static band structure. So that corresponds to this band gap here, right? Then if you include electron-phonon interaction and you remain at 0 Kelvin, so not temperature, just 0 Kelvin, but you incorporate electron-phonon, what you're doing is to actually bring in quantum 0-point fluctuations. So that brings you to this blue line here, up here, and the same for the conduction. So actually, from this point, you jump down and you go to this blue point. Okay. So the band gap that really one is measuring in experiment is the blue point, because in experiments, quantum 0 point is already included, obviously. And the DFT band gap instead is this one, because the ions are classical. All right. So this is a little bit the idea in these calculations. And then you can also crank up the temperature, and you go from the blue line to the red line. The shift in this case is not that big. So you keep basically decreasing the band gap this way. All right. So if you were performing a classical calculation like a molecular dynamics, for example, what you would observe is something that scales linearly until it hits the ground state, static band gap of DFT. All right. Now, these things compare, fairly well with experiments. So these are basically experimental data, the triangles. So you see that there is a deviation between calculation and experiments. So this is pretty well understood now. It has to do with the fact that in DFT, the electron-phonon matrix element are a little bit too weak, okay, because of the small band gap. And that creates a situation where this shift is not as large as it should be, right? So these things will be discussed later during the school. So now let me move to the second bit, which was how wave functions are changing. So I told you that there is a very simple recipe to find out how wave functions change when you have a perturbation potential. So let's see why this is important in phonon-assisted absorption. So as a reminder, if you want to calculate optical absorption, what you do is to look at the imaginary part of the electric function. If we look at the long wavelength, basically, so Q equals 0, you have a simple expression with the optical matrix element here. So valence, momentum, conduction. So this is optical matrix element in dipole approximation. So square modulus, and then Dirac delta between valence, conduction, and the photon energy. So this is the same Fermi golden rule I gave you for the phonons. In this case, is used for photons. Okay. So this is a very standard expression you find in any textbook from Kittel to Yu and Cardona and things like that. Now, in this expression, notice that if you were to do calculation in DFT, valence and conduction would be standard the Constant wave functions, and we are there, right? Now, we know that if we have a phonon perturbation, the wave function is changing, right? So there is this change here. So one thing I could ask is that what happens if I consider this change in the wave function in this expression? So for example, I could write here, instead of this valence state, I could write valence plus delta valence, where the delta is given by this expression. And here, instead of conduction, I have conduction plus delta conduction with this expression here. All right. So if I do that, I'm going to end up with the 4 terms, okay, because I have 2 terms here and 2 here. One is going to be the standard term between conduction and valence, and the other are cross terms: conduction, delta conduction valence, conduction delta valence, delta conduction delta valence. Right. So just to give you an idea, this term usually look like this. You have 2 matrix elements multiplied by with each other. You have valence here, optical transition, intermediate, phonon, final, okay, conduction state. So this is the typical thing that you see in theories of indirect optical absorption, okay, and they come precisely from the fact that the wave function is being modified by phonons, and this is what corresponds to diagrams that you see as undergraduates when we discuss phonon-assisted absorption. You cannot go this way just by photons, so you need to go up with a photon, and then the phonon gives you the extra momentum you need to go to the other side, so you can do transitions that don't conserve crystal momentum. All right. So the way to think about this is that in a periodic crystal, you have conservation of crystal momentum, so only vertical transition in k-space are allowed. But as you consider phonons, they break instantaneously the symmetry, and therefore this transition that don't conserve momentum are allowed. Okay, so this has to do with this change of the wave functions. So you will see much more about this during the lectures on phonon-assisted absorption in much more detail. This is just to give you an idea. And this is an example. These are the experimental data I showed you when I talked about solar cells. So this is the experimental absorption spectra of silicon. This is the calculation you would do using without phonons. Basically, just do a static calculation, and you start absorbing 3 electron volts, which is basically the direct band gap of silicon in this case. And as soon as you activate electron-phonon interactions, you basically have this blue line that captures this chunk that has to do with indirect absorption. So you can do transitions here across the band gap with a different momentum. All right. So you will see these things also on Wednesday. The final example I want to give about these things is about the electron lifetimes. All right. So using the golden rule, we say that one can calculate the lifetime of an electron in a given state, or the transition rate to from a state to another one. Now imagine calculating the transition rate from an initial state, not to only one state, but all possible other states. Okay. So this number is essentially a summation of transition rates, and this is essentially how long an electron stays in a given quantum state. Okay, we call it lifetimes, or the relaxation rate, if you want. So why this is important? You will see a lecture on Wednesday by Samuel Ponce on carrier transport using techniques like the Boltzmann equation. And I mentioned mobility in the beginning. So this quantity here, and this is an extremely simplified version, approximate version of that Boltzmann equation, just to give you an idea of what happens. So you have electron charge, mass of the electron, and something here that does dimensions of this relaxation time that you see here. So this is 1 over energy. This is an energy. So this is a dimensionless number. And if you go doing plots, this is the Fermi-Dirac distribution. This is essentially a very narrow distribution, which is centered near the band edge. So what this mobility is a weighted average of these lifetimes very near the band edges in practice. So that's why calculating these lifetimes is extremely important. And by the way, this is something that if you look closely, is essentially an average lifetime. And this corresponds, so it brings you back to the Dude formula that you might have seen if you study solid-state physics. Is typically, you know, the second chapter in Kittel or something like that. Okay, so all this connects back to what we already know. The difficulty is just to being able to calculate these numbers, and you will see techniques to do that in the next during the week. So this is an example from Samuel about calculations using these techniques, and just to give you an idea of how they compare with the experiment. Though these are lucky cases where things are pretty good. These are measurements of mobility in single crystals of this metal ammonium triodide. It's this object, which is 10 millimeters inside. And these are the Samuel's calculations you see in BTE. So the agreement is pretty good, although calculations overestimate the experiments, which is kind of expected because the calculations only consider phonons as a source of scattering, but there is much more happening in a real crystal. Okay, but this is to give you an idea of what can be achieved at this point with these techniques. So now I want to spend the last maybe 5 minutes discussing some technical aspects that are important to introduce the following lectures. Okay, I mentioned this matrix element, this basically sandwich between the perturbation term that we want to coming from phonons and these Kohn-Sham wave functions. This is a very simplistic way to write it. So there is a much more a practical way, which is what we use in calculations, which is using the block representation. So I need to show you this because you will see these things over and over again during this week. Okay, so instead of having psi m, psi n, we just replace it by block functions, which have both band and wave vector indices. And instead of this potential, it depends only on one atom in one direction. There is something that depends on a phonon wave vector and phonon mode, right? So those two are just the lattice periodic part of block wave functions. And these are pretty easy to calculate. They are very inexpensive, so they don't pose any problem. So what is a little bit more challenging is that it is variation of the potential here. And I'm going to write it in full. It's awful, but you need to see it to understand what we're talking about. So this is the complete expression. I'm going to go from right to left to explain how it works. So this is the change of the self-consistent potential if I move a certain atom K along a direction alpha, that could be X, Y, and Z, and in a given unit cell P. Okay, so I move an atom somewhere in the crystal, and this is the change of the potential resulting from that. Now, this is not the potential change from a phonon. So to have a phonon, I need to have a collective displacement. So this is the phonon polarization that tells me in which direction I need to move the atoms. Okay, so that tells me that this atom moves there, this atom moves there, and things like that. Okay, establish a centered pattern. So those two give me a change of potential according to certain directions, but doesn't tell me how far the atoms are moving. So this information is provided by this term, which is a 0-point amplitude. So once I have the direction, I know now at how far I need to move in that direction. And then there is a last term which is needed to make this object periodic. Okay, so this is all that goes into this kind of calculation. In practice, the calculation doesn't start from this side. It really starts from this side using density functional perturbation theory, as Paolo Giannozzi will explain in the next lecture. The thing I want to mention here is that this calculation is the most expensive part because it is as expensive or almost as expensive as a standard density functional theory ground state calculation. Okay, so each of these matrix elements is something that is quite costly. All right. Now the question is, okay, this is costly, but how many of these matrix elements do I need? Maybe if I need 10 of those, it's going to be cheap anyway. So to explain how many matrix elements we need in general, I want to give you an example. So these are extremely simplified example, but it is representative of all the problems we have with electron-phonon physics. Okay. So in this example, I'm considering the lifetime, so the inverse lifetime or the relaxation rate of an electron. So this is an electron band N in wave vector K. And this is, again, Fermi golden rule. Apart from some prefactors, there is the matrix element squared, the electron-phonon, like in the beginning, and then the energy conserving delta function. That means that to have this transition, the final state and the initial state, they must differ by either plus or minus the phonon energy, right? So let me show you how this works in a simple example. I consider an electron gas in 2 dimensions. So these are parabolic dispersions. And this is a plot, kind of a cartoon of kx here, ky, and the energy. So the dispersion would be this paraboloid, right? So just standard dispersions. Suppose I want the lifetime on an electron that sits on this at this energy, the pink plane. So suppose an electron sitting here, this circle, right? To find this lifetime, I need to consider all the scattering for states that satisfy this equation. Now, phonon frequency is typically very small. So that means that in this plot, all the states that satisfy this relation will be very close to the circle, all right? So in practice, I need to look at all possible scattering possibilities on the circle. Now, let's say that we are very sloppy. So we do a DFT calculation on this density with 4x4 K points. Maybe it's not going to be too good, but, it's reasonable, okay, or acceptable. But if I go doing a calculation, of this kind of quantity with, again, 4x4 K points, essentially what I do is that instead of representing a circle in terms of phase space for scattering, I get, in this pixelated version, I get a square, right? So I'm destroying the kind of the shape of the phase space that I need to describe with this integral, right? So what I need to do really to describe a circle here, to do that, I need many more points. So I pixelate now this the brilliant zone with maybe 40x40, and this pixelation gives me something that starts looking like a circle, okay? So this is the key problem in all problems that have to do with electron-phonon physics, okay? So usually the way to say it more elegantly is that you have a brilliant zone integral, which is volumetric, and these selection rules basically reduce the integral to a lower dimensional manifold. So you go from 3D to 2D, a surface, for example, or from 2D to 1D, okay? So this is really the problem. So you are used to sample the brilliant zone uniformly, like in a volume, but you are describing a surface or a line, okay? So this is a problem in these things. Note this is not only for lifetimes, even for energy shifts, there is a similar problem. Energy shifts don't have the delta function, but have denominators that corresponds to the principal value taken on that, which is basically 1 over energy. So you always have the same things very near whenever you have resonances in energies, and you need a very, very fine sampling of the brilliant zone, all right? So that's the key problem, and that means that we need to calculate this matrix element, for many, many points. So that basically where, 1A functions come into play, and this is something essentially that, came out of a lucky coincidence between many developments in 1A functions that you will hear about in a couple of hours, and this interest in obtaining these matrix elements. So I'm not going to tell you much about this because they're going to be the experts telling you, but the key concept is that if you have a block wave, you can perform some clever trick to extract some localized object out of that, and this object is called a 1A function. And then there are tricks to make this object as localized as possible, and you obtain maximally localized 1A function that will be described by Nicola Marzari today and Antimo Marazzo tomorrow. So you have some reviews here to understand that. But the key point for us is that you can perform unitary rotation to localize your electrons, okay? Now imagine the situation where in the matrix element, I localize the 2 electrons, maybe here and here. And imagine that I can also localize the phonon perturbation, okay? I don't know if that's possible. Let's assume that's possible. So in this case, I would have a situation where the matrix element is really a product of things that might be sitting far away from each other. If that's the case, I don't need to calculate it because it's going to be kind of 0 or very small, all right? So in practice, we don't do calculations in this space, but this is the motivation to establish some interpolation formulas between matrix element and standard block representation and their friends in the 1A representation, all right? So in practice, what happens is one does calculation in this space, transforms and gets these matrix elements, okay? And then does a back transform by padding this with zeros and going back to a very fine space in K space. So essentially, it's like a Fourier interpolation, but physically motivated and in a much more complicated Hilbert space, all right? So just to give you an idea, so this is a vintage picture from 15 years ago, and this was from Diamond. So what this represents is basically how this matrix element decay in the 1A representation. Take a 1A function here, a phonon perturbation, then you take the other 1A function, you move it away. Okay, if you do that, you find that the matrix element goes down exponentially in this case. So that gives you a way to use a few matrix elements or a coarse brilliant zone sampling to obtain what you need. And this is basically shown here. So you do a calculation with 4x4 points, very, very sloppy. and you still get something that after interpolation looks like a standard DFT, density function perturbation theory calculations. So this is why we are kind of obsessed with maximally localized one-wave function, because they're extremely useful for this kind of problems. And this is an example more recent. This is from last year, from calculated by Samuel Ponce, who basically looked at these decays, out of so this was an offshoot from a project on carrier mobilities. Looked at many semiconductors, trying to look how these matrix element decay, and you see basically they're all kind of exponentially decaying for the valence, and there are maybe polynomially decaying for the conduction. So this kind of difference will be discussed by the experts later. And then I just want to also mention one last thing. This is just before closing, that these techniques function work if you can say that the change of the potential coming from phonons is localized. The question is it localized? In practice, one can always move an atom and calculate this potential explicitly, and then you can also formally try to look at how it decays, using a multipolar expansion. This is just standard electrostatics. Okay, so you can always write the potential as a multipolar expansion multiplied by the electronic screening. So basically, how the electrons react to this potential. And the first term is a dipole, then you have a quadrupole, an octupole, and things like that. So this is like a Jackson-style physics. It's nothing to do with quantum mechanics. Okay. So this leads to some challenges, and they are like that. So if you go in Fourier space, so the Q vector notation, this term becomes 1 over Q, the phonon wave vector. So if you go to 0, it becomes infinity. So interpolating this thing is not possible because it's an infinity. It's not smooth. If you look at this one, it is actually not going to infinity. It's of the order of 1, but it is discontinuous essentially. So that creates a little bit of a challenge. And then things start becoming normalized so a bit like milder when you go to octupoles and so on. So this is the potential. So what happens with the electronic screening? So that depends clearly on the material. I just want to give you an idea with a simple kind of scheme. So if you take the two simple kind of expression for the electric screening, so this is standard Thomas Fermi, just electron gas, and this is a modified Thomas Fermi for semiconductors. Okay, so the key difference is that the screening here goes to infinity at Q equals 0, and here it goes to epsilon naught, the electric constant, at Q equals 0. So when you multiply the inverse of that with this expression, so there are two things happening depending on whether you are a metal or an insulator. For metals, all these terms are very smooth, so you can interpolate without any problems. Okay, so things are easy for metals, right? In insulators, things get messy. So this term actually remains singular because you have 1 over Q here, and this term actually does not suppress the singularity, so it still is a constant near Q equals 0. So this remains 1 over Q. So this term remains discontinuous, and then things get easier. So what one does is to develop techniques to remove these problems, okay, before performing the interpolation, and then performing the interpolation on everything that is left, right? So very briefly, I will just show you one example. So this is basically the matrix element of a longitudinal optical phonon in titania, and calculated using density function perturbation theory. You see, you go to 0, Q equals 0, it goes to infinity. So if you try to interpolate brute force without thinking much, you get something completely wrong because you miss the singularity. Okay, so what one has to do is to deal with the singularity in a separate fashion, okay, and then you recover the correct expression. So this is the same problem that you have when you discuss phonons in polar systems. You have the LOTO splitting, okay. If you don't do this kind of corrections, you miss the LOTO splitting, okay. So this will be discussed in the next lecture as well. So this is to say that some aspects are a little bit delicate and they require some attention. So bottom line, what I'm trying to convey is that the basics of the theory are pretty simple, so you don't need to go very far. Then implementation details get a little bit tricky to get all the maths right. Okay, so that's basically the thing. And what I wanted to basically convince you today of, this is a summary, that most properties can be discussed using simple perturbation theory. We don't need to go very far. Okay, a few cases require many body techniques, and we will see them tomorrow. But in many cases, you just are good with standard perturbation theory. The key issue is that we need to find samples of the Brillouin zone to study electron-phonon physics in solids, okay? So this is very different from the case of molecules. And then the third message I hope I conveyed is that maximally localized one-wave functions are very important in this context, and that's why we're going to have a tutorial on that tomorrow, and we're going to have lectures on that today and tomorrow, okay? So finally, I just want to mention some references. You will find these PDFs online, as I said, on the schedule. So essentially, this book is probably the must-read for electron-phonon physics. It's mostly for metals, but most of the concepts are applied to many other cases. So this is a review on some of the techniques I will discuss tomorrow morning. So this is a review on density function perturbation theory. Essentially, is the Bible for these things. And if you want to know anything about that, you need to read that. So this is the review on maximum localized one-way functions. It will be mentioned in the next lectures. Then there are these two papers here from Verdi and Jacques. These are basically papers where these techniques of dealing with this dipolar singularities are discussed. Okay, you can take a look if you're interested. And these are more recent papers by Brunet and Gialani, where they looked at what happens to the quadrupolar terms, and these actually appeared very recently, a couple of years ago. So these are all references that you might need to if you want to dive into these kind of problems. Although you might not need all this level of specialization, but the references are there for your consultation if you need to. All right. So this is the end of the lecture, and I think I'm going to stop here and take questions if you have any. All right. So questions. Yeah, go ahead.
Slide number 13.
Yeah, just you need to open to switch on.
Thank you. So you said that for the large temperature, these two expressions are the same. But I see that in the quantum case, if the temperature is very large, you end up with just h bar over 2m omega. While in the classical case, you don't have h bar and over omega squared.
So basically this h bar and this, so basically what happens at high temperature, this h bar and this h bar, they cancel out.
Isn't that high temperature that the first term is 0?
So at high temperature, I mean, actually, we can do the maths together, but so the high temperature limit of this expression is the one above. Okay, so you can just check it out. Okay, I see. So I think, yeah, what Zeglu is saying, this is actually the variable of this distribution. Okay, yeah, thanks.
Hi. So on stage slide 27, we were talking about the dipole and quadrupole materials. What happens if you have something that's like a quasi-2D material in the sense that it's metallic in one plane, but insulating the other? How do you kind of disentangle those effects when trying to analytically deal with these dipole terms?
So I don't know what is the answer there. I think it can be worked out. So typically, let me tell you how people work these things out in general. So the way one does is to very simply write down this monopole, this dipole, and all these things. Sorry, dipole, quadrupole, and then do the electrostatics very simply using the same techniques that one learns in E&M basically. And then does some expansions of this dielectric function, essentially. So I think the same thing will be done in that case. So that's the way actually some of us did expansions of this kind for 2D materials. I mean, actually, the ones for insulating materials are quite, in the past 5 years, I think they emerged. So I think how to do 2D materials, which are semiconducting, is known now. How to do semiconducting things in one direction and metallic in direction, I think one has to work it out, but I think it should be doable. It's more that basically all information that will be present into the dielectric function of the system. Okay, so I don't think, I mean, it doesn't exist at this point, but it should not be problematic. I mean, it's just a matter of doing the maths.
Okay.
Yeah.
I have a question about out of equilibrium displacement. You said shining light will lead to shining one mode as well, but I think that is for optical phonon. So for acoustic phonons, what are the ways to make them run?
So basically, well, I mean, I guess you're asking how to excite acoustic phonons. I mean, I don't want to go there. I think so what I'm trying to say is that here, there are two scenarios really. One is you are interested in equilibrium, and the way to do that is to just apply a canonical average to whatever you find, In the case of auto equilibrium, one has to decide the kind of experiment is being performed. So in that example, so you pump optically, an optical phonon is very well defined. So you will have some kind of oscillations according to the pump frequency. For other situations, one has to discuss it with the experimentalist essentially. So at that point, so that becomes in a way, let's think about that in these terms. It is an input parameter, is an external input to the theory essentially. So there is no general. So that's why I didn't want to discuss it, because in the case of equilibrium, well, there is only one equilibrium. So I mean, at least if we think about canonical ensemble, in the case of auto equilibrium, there are many possible implementations. So the point in that case is that if one finds out, what these displacements are as a function of time, then one follows with this kind of expressions, and then works out the consequences. Okay. So I guess you have in mind, your coherent phonons and things like that. I think all of this can be done. I mean, you just want us to specify exactly what is the kind of time evolution of these coherent modes. Yeah. Thank you.
Yeah, I'm just continuing with the previous question. So talking about the two-dimensional material, like about the screen, do you consider like the truncation, the quantum truncation along one direction, like something like that, like you have two-dimensional material, this direction in the two-dimensional direction that extended, but the vertical direction main event of iterate, so this is something like the quantum truncation along that direction or something.
Yeah, I mean, so that's that is a technique that is used. So if you model a 2D material using a supercell, there is this problem that the adjacent layers they feel the Coulomb interaction between themselves, and this is long range. So one way to avoid that is to truncate the Coulomb. This is the same technique is used in GW calculations on finite dimensional systems. So that's always possible. It's not a problem, but one has to still be careful about what are the implications of these choices on the electron-phonon matrix element, essentially. So long as the theory is internally consistent, it's all fine. Okay.
Thank you for this wonderful review on this topic. So I have a question about complexity-dependent base effect. And you talked about and you explained the motivation. I'm thinking if there's any consideration of expansion of lattice, maybe we do like not
yeah, that's there is. So the way things were done in actually in the early days when people started doing these things, that was the only effect that was considered. So you do a quasi-harmonic calculation and to look at how the lattice expanded the bus structure. So that's one effect essentially. So this is another effect. So at least to lower the perturbation theory, they adapt essentially. So one has to do both. So that's the idea, and that's how one can do these calculations. So so in this case, for example, in the case of silicon, lattice expansion is very small, so it doesn't matter in these calculations. If you go, for example, to gallium arsenide, already it matters. So what one has to do is to apply these kind of techniques for each temperature, but also not for the standard kind of ground state structure, but at each temperature one has to use the structure coming from quasi-harmonic or from experimental kind of lattice parameters. So both of them have to be considered to be accurate. Yeah, that area.